morning, everyone. I'm Tomiko Brown-Nagin, the Dean of the Radcliffe Institute for Advanced Study at Harvard University. Welcome to our annual Science Symposium. Let me begin with some thanks. First of all, I'm grateful to the speakers who are here today and participating in today's symposium. Thank you for taking the time to be here with us. Many thanks also to Alyssa Goodman, who conceived today's program and will offer opening remarks in just a few minutes. I also want to express thanks to Rebecca Wasserman, who is the Executive Director of our Academic Ventures program here at Radcliffe, and also to Jessica Vicklin, who is the Director of Events. I will also thank the entire team in Academic Ventures and Events for organizing this very exciting program today. I also want to acknowledge members of the Radcliffe Institute Leadership Society and our dedicated annual donors. It's because of you that we're able to organize events like this and open them free to the public. Thank you. I'm also delighted to note that we're joined by a number of students today, including more than 40 from Barnstable High School, who are here with their astronomy teacher, Michael Gyra. We'll get to hear from a couple of, yes. Right. We'll be able to hear from a couple of those students later in today's program. Today's symposium will explore how scientists across a range of fields tackle the undiscovered in order to advance new knowledge. We're getting a behind-the-scenes look at how science really works. Generally speaking, there's a chasm between the way scientists do their work and the way the rest of us tend to imagine it. Among non-scientists, there's often the impression that scientific discovery results from a linear process of hypothesis, formulation, empirical observation, and accumulation of cold, hard facts. That this view is so commonplace isn't surprising. It's called the scientific method, and many of us grew up learning it. But the actual practice of science is far different. Hypothesis formulation and empirical observation are critical, to be sure. But as we'll hear today, unpredictability, leaps of faith, the element of chance, and rigorous preparation for the wholly unanticipated are equally important to scientific discovery. The work of scientists is complex, dynamic, and creative, not formulaic or rote. Our first keynote speaker, Stuart Firestein, has compared scientific work to searching for a black cat in a dark room when very often there is no cat. Today's symposium provides an opportunity to explore what exactly this means in practice and to consider the implications for how we as a society understand and value the real work of science, how we support scientific discovery through research funding and public policy, and how we prepare students to become the path-breaking scientists of tomorrow. I encourage you to learn more about this last point by visiting our student poster session over lunch. Today also is an opportunity to take advantage of Radcliffe's remarkable interdisciplinarity and engage in exploration across academic and professional boundaries. I think it's safe to assume that we each have a more nuanced understanding of our own disciplines than do our colleagues or peers in other fields. The natural sciences provide a particularly stark illustration, as we will see, but more generally, we should never hesitate to ask one another to explain how we go about our work and why. We can learn a lot from those answers. Now, I'm pleased to turn things over to my colleague, Alyssa Goodman. Alyssa is the faculty co-director of the science program at the Radcliffe Institute, a distinguished scholar whose important work spans several fields. Alyssa also serves as the Robert Wheeler Willson Professor of Applied Astronomy in Harvard's Faculty of Arts and Sciences. And now, Alyssa.
Well, thank you so much for coming, and thank you, Tomiko, and thank you so much to Radcliffe for making an event like this possible. I should say that I've been at Harvard for a very long time, and I've only been affiliated officially with Radcliffe for a few years, and that started with the Radcliffe Fellowship Program. And some of you in the audience have had the privilege of being a Radcliffe Fellow. And I'll just tell you that if you enjoy today, pretty much that's what being a Radcliffe Fellow is every day. So it's really terrific. So I think I have some slides to show you to try to explain what really is going on here today, because a lot of you may be thinking, this looks cool, but I don't know, what is the Undiscovered? What is this symposium about? I will fix this for you with literally one word. Are you ready? Okay, now watch carefully, right? Okay, you got that? Right? I don't know, and saying I don't know, and I have no idea, but I'm going to try and act like a scientist and figure it out, is actually what this symposium is about. And I should say that the original idea was actually to focus this completely on education and communication, and to change the way that science is perceived by the public and the way that it's taught in schools. And we decided actually in the end that the best way to do that is to demonstrate the way science is actually done, and to have a focus on education in the poster session that you heard about at lunch. So we'll explain the details of, sorry, not at lunch yet, sorry, it will happen at lunch. And we'll explain the details of that in just a minute. But before I continue, I thought I would give you one small example of a story that just encapsulates the undiscovered in one tiny vignette. And it's actually a story that has a lot to do with my friend and former colleague here, Bob Kirshner, who will give a lecture in the Undiscovered series, which is described in the back of your program. So if you like what you hear today, there are many events over the course of the year, some of which have already happened, one of which I'll mention in a minute. But Bob Kirshner, as many of you know, is a very prominent astronomer who is involved in something called dark energy and the discovery of dark energy. And what happened was, a lot of you know that the universe is expanding, and that's called Hubble's law. And the thought was that that expansion should decelerate. If you could measure really, really accurately the galaxies moving away from us and from every galaxy, what the speed of that motion is exactly, that you could find a deceleration. So two teams, a team that involved Bob here at Harvard and another team led by Saul Perlmutter, went out to do this. And they had a very carefully designed experiment. So as you just heard Tomiko say, it's not that what we're talking about today is total serendipitous luck. We're talking about when you have a plan, but you don't usually find exactly what you plan to find. And in that particular case, they went out to measure the deceleration of the universe, and they found the acceleration of the universe. And Nobel Prizes were awarded as a result. Okay, so that is a perfect example of the undiscovered. You do very careful work, and occasionally you don't just find something surprising, you find the opposite of what you set out to find. Okay? And so this, to us, is what gets us up in the morning. Not that we never think we're going to find what we planned, but the idea that science is so exciting and that it's undiscovered, that it's the stuff that isn't found out yet that is really interesting. And I have another quote that is actually my favorite. And you say, why could Socrates, Albert Einstein, and Barbra Streisand be on the same slide? And the answer is, if you research this quote, they've all said it. So have many, many other people, including me. Okay? And so if you think about this, the more I learn, the less I know. What that means is the more you become expert about something, the more you realize that there's a whole lot more to know, and we don't know very much. Okay? And so the people who you're going to hear from today are experts on a wide variety of scientific fields, and you'll hear them, hopefully, be extremely honest with you about what they do. And so we've tried to divide the program into kind of three sections. So we'll have a keynote in the morning and another one at the conclusion, and then we'll have a series of other talks and panels that focus roughly on what we're calling Earth, life, and space. But because of the interdisciplinary nature of the work being discussed, I couldn't even put everybody in the right categories. Okay, so some of them kind of bridge what's going on. And so to just give you a little taste, when it comes to Earth, Nate Holtman will talk about energy and environment and policy and science and the mixture of those things and how the undiscovered plays into that. Stuart Firestein, who you heard a minute ago, will be our first speaker, will tell you about his ignorance project. And he himself works on neuroscience, so I put him between Earth, where we're ignorant, and life, which is neuroscience. Jill Tarter, who will be our last speaker today, is probably well known to many of you as the real person upon whom the Jodie Foster character in the movie Contact is based. And if you've seen that movie or read that book, you know that Jill has dedicated her life to a very systematic search for radio signals from extraterrestrial life. Speaking of extraterrestrial life, let's go around in a circle. When it comes to space, and also life in space, we have two experts with us today, Laura Kreiberg and Lisa Kaltenegger. And they'll talk to you, both of them, about possibilities for what we might find on planets around other stars in terms of the properties of the planets and life there. Joel Dudley, squarely in the middle there in terms of life, is actually going to tell you about what happens when you take huge amounts of data and look for things that have to do with life, but don't always find what you're looking for. And I'll just leave it there. And then Wally Fulweiler is shown there as bridging Earth and life, because she's going to talk about coastal ecosystems and the effects that we have on the chemistry of those systems, and then the effects that that chemistry has back on life. So hopefully you see that this is kind of a very interconnected web. And I'm very pleased that several people are going to participate, local people, as discussants. And so the way that this will work is people will give talks. These discussants will have time to ask their own questions, and then you, the audience, will be asked to participate. So the biographies for all of these people and all of the speakers are in the program that you have here, but I'm just going to say that I'm honored to have Conaveri Valencias from Boston College here with us for the Earth session, Immaculata De Vivo, who's my co-director for science this year here at the Radcliffe Institute for Life, and David Charbonneau, my colleague in the astronomy department, to tell us about space and extrasolar planets. So I just want to leave you with one request. This is an article that was in the Harvard Gazette recently about the ship Tara. Is anybody here, were you lucky enough to see Tara when it was visiting? Just raise your hand. Okay, so a bunch of the fellows and a few of you. So what Tara is, we brought Tara here because Tara was one of the projects that actually inspired this whole undiscovered theme, that and Stuart's famous talk he's going to tell you about in a moment. So what did Tara do? Tara is a ship that's sponsored by a French cosmetics company. And one of the projects it did recently was to go around the world and gene sequence all of the plankton that they could find in the ocean. And they took the number of known species of plankton from 15,000 to 150,000. So if you think that what we know about science is in books, the whole goal today is to encourage what maybe we should call out-of-the-book thinking, okay? And we want to start a conversation both here at Radcliffe, at Harvard, with educators and with the public, that science is not solved. It's not boring, it's not dry, and most of it is undiscovered. Okay? So that's what I would like to say, and then we're going to have a very special invocation of our event, and that's going to come from Ceili Magnus, who is one of the students from Barnstable High School, which Mike Gara was so kind to bring here. And he brought to my attention a poem that she wrote inspired by Stuart Firestein's work. And we're going to have her read her short poem, and then we'll go on to Stuart Firestein, and hopefully you'll very quickly see the connection. So Ceili is an amazing student who's interested in both science and the arts, which really embodies the spirit of Radcliffe. And I'm really pleased, and I hope that we can welcome her here now. Thank you, Ceili.
Hello. This poem that I wrote is titled Method versus Muse. People have drawn a thick line between art and science, but what is science without the arts? The questions that need to be asked can't come from a formula when for centuries they've been deeply rooted in the hearts of geniuses and prophets with brains full of thought. It seems that over time, humanity forgot how to think critically and to question with care, because in an age of internet access, the answers are always right there. And schools are so focused on students having all the right answers that they forget that we're poets, designers, and dancers. They drop facts on young minds like piles of heavy bricks and expect us to absorb information stacked miles thick. They teach us so much, but now we need to build from it. They've marched with us to base camp, but our goals are at the summit, applying what we know to explore the unforeseen. The undiscovered is easier said than done when curiosities lie dormant and smothered. Because every day I see young minds afraid to ask questions. It cripples the scientific world at its very foundation, and research never comes without curiosity, without a spark. And my spark would have died too, but I found my light in the dark. My creativity led me to ask all the right things, and now I stand here before you to ask, when will you change the tune that you sing? What will it take for schools to open their eyes to a world of unmatched opportunity that very clearly lies in the minds of young people who still have their fire? When will you take their thoughts and lift them up higher? Maybe you will be the one to inspire someone's great questions or someone's desire. Teach young minds to fall in love with the unknown, because for every question we ask, there are many more to go. Nurture the creativity we all harbor in our hearts, and maybe we'll give way for a new way of thinking to start. Thank you.
I can't thank you enough, Ceili. That pretty much sums it up in 3 minutes. And Stuart's got a hard act to follow. So as I mentioned, as I mentioned at the outset, we have the biographies of our incredibly impressive lineup of participants today in the program that you have. And we're just going to give you a couple of little reminders of who each person is as we go along. And I'm sorry, but if we went through all of their accolades, that would take the whole time today. So Stuart Firestein is a professor at Columbia University who technically teaches neuroscience there, but he also teaches ignorance. And today he's going to teach us about ignorance. And just to say a couple of words about his scientific research, he studies the olfactory system, the sense of smell in vertebrate animals. And he'll explain how he started teaching about ignorance, but I'll just tell you that I love the title of his 2 recent books, both titles. One is called Ignorance, How It Drives Science, and the other one is called Failure, Why Science is So Successful. And so I'll just leave it there and say thank you for coming, Stuart, and we can't wait to hear what you have to say. Thank you.
Well, this is quite a crowd. So I owe great thanks and appreciation to the organizers of the symposium, to Dean Brown-Nagin, even though she stole my first 3 slides, to Alyssa Goodman, who stole my second 4 slides, and to Ceili, who stole my whole talk. Nonetheless, I'm thrilled to be here today, and it's so nice to see such a large group of people come out for this as well. So let me preface this to some extent by saying I don't think I'm actually going to tell you anything you don't somehow or another already know. I think the idea that science is about ignorance and about failure in so many ways is something that we almost all know in a kind of implicit way. What I hope to do today is to take those ideas and make them explicit, because I found that by making these things explicit, we get to re-examine them in ways that we may have forgotten about, and that new things show up in that way. So I'm going to talk about ignorance, doubt, uncertainty, and failure, which sounds pretty existentially bleak on a beautiful Friday morning, but with the I hope, aid of PowerPoint, we'll turn these things into more positive ideas. So that's the notion here, that science is successful, and many other things in our lives are successful precisely because of these things, and that they're not typically or should not always be understood in their typically pejorative manner. So we might ask, how successful has science been, in fact? Well, this is a picture of the Acheulean hand axe. This was the first tools made by human beings, as far as we know. This technology lasted for some 1.2 million years. All right, that's kind of a long time for one technology. But we could go a little further forward. Most historians or historians of science believe that the Bronze Age is really kind of the beginning of science, if you will, or the beginning of some kind of historical science, in that bronze can't be taken out of the ground. It has to be smelted. There's a process involved. But the Bronze Age also lasted for about 2,000 years or some 50 generations. So for 50 generations, people just like you and me with the same brain inside their head were born, grew up, and died in precisely the same technology. Now, you know, today, if you take a 2-week vacation, you're like 2 operating systems behind and hopelessly out of date. So clearly, things are moving a little faster, and that's primarily happened since what we typically call the scientific revolution, about which there's some debate and all that, but I'm going to call it the early 17th century, beginning with people like Bacon, Descartes, Galileo, and so forth. And now for the last 10 or so generations, a mere 400 years, we have these iconic equations, just some of many, but what's particularly interesting about these equations is they not only work here on the Earth, but they're true throughout the entire universe. And that's a big step. That's a big intellectual leap forward. We also know, of course, that there are huge advances in technology and transportation and communications and flight and so forth. My own particular favorite, because I was trained as a pharmacologist, is in pharmaceuticals. So, for example, we have this stuff here. I don't know how well you'll be able to see it from the back there. It's one-night cough syrup, it's called. It has in it alcohol, cannabis, chloroform, and morphine. Thus, I believe the name One Night, where that comes from. There's also Dr. Batty's asthma cigarettes for the treatment of various bronchial disorders and so forth. The big advance here, which I don't know if you can see at the bottom, is that there's a warning label here, actually. These are not recommended for children under 6. So you can see that we move forward in science. Progress is the key to science. How do we make this progress? How does this all come about? What's the actual method? Well, Dean Brown-Nagin has told you a little bit about my idea about this. This is an ancient aphorism. It's anonymous. And it says, it's very difficult to find a black cat in a dark room, especially when there is no cat. But I just find this a very apt description of what we do in science. We fumble around in dark rooms, we bump into things, we feel around, we imagine what it might look like, where things are, where the cat might be hiding. And whether we find the cat or not, we move into another black room. So if we find the cat, that's fine, then we just find another dark room. And if we don't find the cat, well, we move into another dark room and look for another black cat, which is, I think, why scientists tend to be so pale. Maybe. It's one idea, anyway. But that's contrasted with this notion of the scientific method, which we're all sort of taught in school as how science works. And I have a whole rant about the scientific method that I will try not to get too deeply into, but I think it's a very wrong idea. It's a wrong idea because there's nothing particularly methodical or recipe-like about doing science. I mean, really, it's more like this, to be honest with you, and kind of like that. So let's compare the scientific method for a moment to what I think the process is more like. So here's the scientific method. You make an observation, you come up with a hypothesis about what might be causing that observation. You do some test or experiment you've devised, you make a new observation, you revise the hypothesis, and so forth and so on, in some iterative way. The trouble with this idea is that the key thing, which is hypothesis, come up with a hypothesis, it tells you nothing about how to do that. It tells you nothing about that process. What do? Find the book of hypotheses and we'll look a couple up. Oh, this one looks good, we'll try that. So how do you come up with this hypothesis? So instead of a scientific method, I'd say what we really want to do is think about a scientific process. And that process starts with ignorance, something we don't know. There's often some kind of intuition about that thing. We do observations, experiments. They almost invariably fail at a high rate. So now we have a new question. We make a question up. We try some inspiration on this question, some imagination. Usually that fails. So we revise. We have an interim explanation. That typically fails. And eventually we wind up with yet a better question. Thus the scientific process. And that's where we end up with. And I think this is what this is why we have made the kind of progress we have. So I'm going to try and prove that to you in a way. This is a favorite slide of mine and a favorite quote of Marie Curie, who, after obtaining her second graduate degree, so she knew a lot of stuff, right? But still says one never notices what has been done. One can only see what remains to be done. And I thought it's what the remains to be done that's so lacking in our education and our thinking about science, because that's really what scientists think about. When I go to a scientific conference, I sit through a long day of boring talks, and then I head for the bar where I learn the real stuff. And what I talk about at the bar over a couple of beers with my colleagues is not what they know. Nobody cares about what we know, but what we don't know. What are the questions? What remains to be done? And I thought, well, this is maybe something important to think about. Just in passing, I have to note again that this is one of my favorite pictures of Professor Curie, because I am convinced that that glow behind her is not a photographic effect. I think that's actually the real thing, you know. In fact, today her papers, her notebooks are so hot that they're stored in a basement room in the Bibliothèque Nationale Française in Paris. It's lead lined, and if you're a scholar and want to go work on her papers, you have to wear a radiation suit. So, I say this not just as a joke, actually, but because it's a serious issue here. I think one of the ideas that's often left out of science, just as a side remark, is courage. And I think this is a real case of courage. I mean, Marie Curie knew what was going on and knew what that was all about and what the dangers were. And I think there's a lot of science that's dangerous in many ways, whether it's intellectually or physically, and it requires a certain kind of courage that we often discount in its practice. So, as was also pointed out, I think, by one of our introducers, that the thing about ignorance is that it grows with knowledge. That the more you know you don't know. And I like this sort of, this is not original with me, several people have come up with this kind of model. If you think of knowledge as that bright white circle in the middle of this sea of ignorance, then, you know, there's this is the only formula in the talk, I promise. But you know that the circumference of that circle, the part of it that's in touch with all the vast ignorance, is described this way. And as that circumference, as that circle grows, as the amount of knowledge grows, so does that circumference by about 6 times the radius. Also grows. And so we increase our ignorance as we increase our knowledge. I think this is an important process to think about. We typically think that we begin with ignorance and we go to school, we read a book, we do something, and we gain some knowledge. But then the crucial question is, what do we want to do with that knowledge? I mean, it's useful, knowledge is useful, but what do we want to do with it? And I think the thing we mostly want to do with it is make more ignorance. But not just any ignorance, we want to make better ignorance. We want to make higher quality ignorance, if you will, because, you know, there's low quality ignorance and there's high quality ignorance. It's not all the same, right? I mean, we argue about this. This is what scientists argue about. Sometimes they're just bull sessions, sometimes they're grant proposals, sometimes it's not clear which they might be, but nonetheless, it's what we argue about, the quality of the ignorance, or if you will, the questions. So the idea of knowledge is to pose a better question, a more sophisticated question, a deeper kind of question. I'm going to use a story here about I.I. Rabi, a famous physicist who won a Nobel Prize in 1944, was it, for the development of nuclear magnetic resonance, a technique that's still very important in chemistry laboratories, especially today, and gave rise to the medical diagnostic tool, magnetic resonance imaging. And Rabi, who was a professor at Columbia, but I never knew him, he passed away before I got there, used to tell the story, apparently, that when he was growing up, I think it's important to say today, as a young, as a young immigrant child on the Lower East Side of New York, that he and his friends would come home from school and their mothers would all say, "So what did you learn in school today?" But Mrs. Rabi would say, "So Isidore, did you ask any good questions today? Did you ask any good questions today?" was what Mrs. Rabi wanted to know. And Izzy here won the Nobel Prize. I don't know what happened to his friends. I'm sure they did okay too, but I think Mrs. Rabi had the right idea. So one of the things that happens when you write a book, I learned, I'd never written a book before. I write scientific papers that nobody reads, and then I wrote a book that people did read, and then they send you letters, or in this case, an email. This is from a woman named Kathleen Erickson in Minneapolis, Minnesota. I don't know Kathleen, we've never actually talked, but she read my book and wrote me this interesting letter. One of my grade school arithmetic teachers began the first day of class with this statement: "I assume all of you learned your multiplication tables through 12. So we waited while all of us sat frozen because we'd all learned our tables through 10. Terrified that he'd spin around, point at me, and say, 'Quick, 7 times 12. I raised my hand and admitted that I'd only learned my tables through 10. He then asked the rest of the class how many had learned their tables through 10, and of course, everybody raised their hands. All right, he said, looking at the raised hands, Kathy gets an A from me this year because she's just learned the one thing that is essential to learn, when to say, I don't know. And Ms. Erickson says, this lesson remains the single most useful experience in my educational history. So a word to the wise from Mrs. Robbie and Kathleen Erickson. So when I say ignorance, of course, I don't mean just garden variety ignorance. I don't mean stupidity or a callow indifference to facts or things like that. I mean something, this was a quote from James Clerk Maxwell, possibly the greatest physicist between Newton and Einstein, who said, thoroughly conscious ignorance is the prelude to every real advance in science. This notion of thoroughly conscious ignorance, not just, I don't know, not just, I wish I knew that, but rather this thoroughly conscious ignorance. How do you get to that? Well, I found an interesting phrase. It was pointed out to me by somebody in this search for better ignorance. The phrase is called negative capability, which at first sounds like a bit of an odd idea. This word was coined by the dreamy-eyed poet John Keats, in fact, also in a letter to his brother, where he identified the word as meaning that is when a man, maybe we should say person, is capable of being in uncertainties, mysteries, and doubts without any irritable reaching after fact and reason. And it's this notion of being patient with mystery, with uncertainty, and doubt. And Keats considered this the ideal creative state for the literary mind, but I would say it's just the ideal creative state for any mind. That when mystery, doubt, and uncertainty surrounds us, this is when we become most creative. This is when we think the deepest and the hardest. And so to learn to be patient with this, to develop negative capability, I think is one of the critical things that we would like to develop in students and ourselves. This was sort of said similarly by a scientist, in fact, Erwin Schrödinger, who I guess knows something about cats, or doesn't, I guess, as the case may be, right? I think about it. So Schrödinger said, in an honest search for knowledge, you quite often have to abide by ignorance for an indefinite period. Again, this notion of being patient with ignorance. All right, so I've taken you a little bit through ignorance. I hope you believe that the unknown is very important. But now, what about a deeper kind of ignorance? What about a really deep kind of ignorance? What about the unknown unknown? What about the stuff we don't know? So kind of ignorance squared, as it were, right? This most recently, unfortunately, was said by this guy, and so there are enough people in the audience who recognize this character. For those lucky group of you that are much younger, this is Donald Rumsfeld, who was the Secretary of Defense and the architect of our misbegotten adventures in Afghanistan and Iraq. And he was called to testify at the Senate as to what had gone so wrong. And he said, well, there were a lot of things we didn't know. We knew that we didn't know them, but we tried to deal with them and all that. But what really got us there were these unknown unknowns, the ones we don't know, we don't know. He was roundly ridiculed for this, but it's actually a clever statement. Unfortunately, he's not the first person to have said it. I learned it actually appears, to my knowledge, earliest in a long epic poem by D.H. Lawrence called New Heaven and Earth. I don't actually care for the poem, to tell you the truth. It's kind of long, goes on. But in any case, it's about the transition from this life to the next, if you will. And towards the end, there's a verse that goes, now here was I, new awakened, with my hand stretching out into the unknown and touching the unknown, the real unknown, the unknown unknown. So how do we get to this unknown unknown? How do we get to this really deep kind of ignorance? And I would say one way, maybe not the only way, but one very successful way is through failure. You go to do an experiment because you don't know something. You think you'll know something at the end of the experiment. Instead, the experiment fails. It doesn't work. So now you know that there was something you didn't know before you started the experiment, right? You understand what I mean? I think I got that right. And so what about this failure? How can we use it? This is a quote from Benjamin Franklin, arguably America's first scientist, who says, perhaps the history of ours of mankind, all things considered, more valuable and interesting than that of their discoveries. After all, the truth is uniform and narrow, but screwing up, I mean, there are just endless ways of doing that, right? And so it's far more interesting, of course, than just truth and success. So there are a lot of ideas about failure, and I'd like to say none of them are the ones I want to talk about today. So I want to put them up very quickly just so we get rid of them. They're useful things if you have someone on the phone who's just had a terrible failure in love or sport or business or something, and you want to pep them up or tell them something. So here are a couple of those. Success is learning to fail again and again with no lack of enthusiasm, often attributed to Winston Churchill, who in fact never said it. But he gets lots of credits for things he never said. Fail hard, fail fast is a favorite in the tech industry. But this is this notion of just get rid of failure. Just get rid of it and get on with your success. This was said by Thomas Edison upon inventing the light bulb. He claimed to have discovered 10,000 ways it didn't work. I think he's exaggerating a bit. I find it funny also because like the light bulb going off, so, oh, that's a good idea. But he failed at that like 10,000 times. You know WD-40, the lubricant that everybody uses to fix everything apparently? The reason it's called WD-40 is that there were 39 earlier versions that were no good, didn't work. Failure is an opportunity to begin again more intelligently. Oh, this I actually got in a fortune cookie in a Chinese restaurant, so I figured I'd take a picture of it. Failure is an opportunity in disguise. And this is one of my favorites. If you're 40 years old and never had a failure, you've been deprived. That was said by the actress Gloria Swanson. I'm not really sure what she means there, but it's interesting. Nonetheless, I don't mean any of these kinds of failures. I don't mean the kind of failure that just promotes resilience or from which you learn something, from which you gain some, I don't know, good personality trait eventually or something like that. I'd rather take a somewhat more enigmatic statement from Gertrude Stein, a poet, who said, a real failure does not need an excuse. It is an end in itself. So imagine failures that are just ends in themselves. It's not because, oh, I didn't think this through, or, oh, I'm sorry, I made a terrible mistake, or this is screw up, or this or that. No, this is just an end in itself. It's worth thinking about that, I think. Also from the ever enigmatic playwright Samuel Beckett, ever tried, ever failed, no matter, try again, fail better. And this sounds so much like the regular old failure trope. I tried, I failed, tried again. But then he says at the end, fail better. How does one fail better? So failures in an end in themselves and the idea of failing better, I think, are crucial things to try and wrap our mind around. So what I'd like to say is that failure is not only valuable retrospectively because it eventually led to success or some serendipitous discovery. I mean, I think those are all fine, but they're not a requirement for failure to be valuable. Failure is an integral part of the fabric. Especially in science, it's integral to the process. You can't leave it out or avoid it, but you can utilize it, and you can improve it. You can get better at it. You can make it better. So we could ask a couple of reasonable questions about failure. One would be, how much failure? I mean, probably not 100%, but I do believe we regularly underestimate, significantly underestimate, the amount of failure that would be acceptable. So I'll use as an example from the natural world, since I'm in the earth part of this thing, or the life part of this thing anyway. Here, these guys are all the top of the food chain. They're evolution's winners, as it were, right? They're the kings or queens, if you will, of their particular niches, the air, the sea, the land, etc. And I'm sure you believe, as I did for a long time, that anytime they get a little hungry, they just go out and bag a snack, right? But in fact, that's not the case. There's a vast literature on this, the predator-prey literature, and in that literature you will find that these guys here are successful on fewer than 25% of their attempts. 75% of the time, they fail. That's why all those prey animals are still out there roaming around, right? So apparently with a 75% failure rate, you can still be the top of the food chain, if you will. Since we're in World Series, is the World Series going on? There is one, right? I'm sorry. I'm from New York, I lost track. I'm sorry. So, you know, our two sister cities sport two of the greatest hitters of all time in baseball, sported two of the highest lifetime batting averages. But, of course, they also both failed about 65% of the time. And as those of you who know baseball today will know that any hitter who hits 300 or above is likely to be sporting a $14 million plus yearly contract. So with a 2/3 failure rate, you can do pretty well, apparently. So I think we, as I say, significantly underestimate the amount of failure that's acceptable, and that's important because this failure is valuable. These failures are valuable, and so we shouldn't. Yes, we don't want to try and exclude them. Now, this is the obligatory New Yorker cartoon, but it is true that one of the things that it would be more fun. I don't think golf is fun anyway, frankly. I don't think there's anything you can do to golf to make it more fun, but it certainly would be improved. Yes. So we do this regularly, and the important thing here, of course, is that failure, in this perhaps slightly counterintuitive way, also gives us a certain confidence in the occasional success. So if you fail quite a bit, or a failure is part of the process, then you don't have an infallible process, as it were. You have a very fallible one, and that gives us confidence that when we do succeed, we have actually made some sort of an important step. So failure and struggle is actually quite critical to the process. Another question we could ask is how big a failure. So I'd say let's go for the moon here, and how about a debacle, right? So a debacle is currently defined as an unmitigated disaster, total failure. But the word has an interesting etymology. It comes from a French word that's not really in common use anymore, débâcler, which means to free, to unbar, or to unleash. And its original meaning was in a nautical term, ice breaking. So the notion of breaking up something solid to provide new pathways. Oh, that doesn't sound so bad, does it? That begins to sound interesting. And so we often think that creativity or innovation or things like this arise from associating new ideas. But I think quite often they also, maybe more powerfully, arise from dissociating ideas that have been too long associated, which we no longer think about having been associated, but which need to be broken apart. The famous philosopher, Spanish philosopher of the last century, Ortega y Gasset, said it costs more to dissociate ideas than to associate them. So I'd say, let's have a breakthrough, right? I mean, we still use this word for a big discovery, and yet it has the word break in it, right? So I think this notion of breaking things up a bit is also very valuable. So you can have a fairly big failure, and it can be quite useful. All right, so I'm going to leave you, I'm not finished yet, but I'm going to leave you with two key ideas about ignorance and failure. Negative capability, this notion of remaining in doubt and uncertainty, but having patience with mystery and ignorance. And then failure is an end in itself, and one can learn to fail better, as it were. I think those are two key ideas, and I see them as related. So, along with failure and ignorance, of course, comes uncertainty and doubt, and we've sort of mentioned these a little bit, so I just want to talk about them for a quick moment here. I call this slide the problem of certainty and the value of uncertainty, because I think we often reverse that idea, and I'd say we're wrong about that. So uncertainty is something that in many areas of our life we like. I mean, if you're playing poker, or you're at the casino, or you want to watch the baseball game tomorrow night, you'd rather not know the outcome before you watch the game. Well, it's kind of less interesting. We have these spoiler alerts. I'm guessing nobody in this room probably wants to know the exact time and date of their death. Who wants to know that? Kind of ruin the party, I think. But these kinds of uncertainties, I would also say, have a fundamental difference with scientific uncertainty, because they will, I guarantee you, they will all resolve. The hand will be shown, the ball will fall, the game score will be posted, and I'm sorry to say that in some digital place or another, the exact time and date of all of our deaths will indeed be recorded. I find there's a kind of a grander uncertainty in science, where there may be no ultimate solution, no final resolution, no guaranteed complete answer. That this is a kind of, if you will, endless frontier. That indeed, the purpose of science is not to get to 0 or 1 by doing more and more experiments, but to develop what I would call stable probabilities, a stable kind of uncertainty that we can then work with and do work with in quite important ways. So the question to me is not how we become certain, but how we get on so successfully while accepting uncertainty, which is what science traffics in to a large extent. And certainty, if we reached it, would kind of be the end of inquiry, which doesn't sound very good to me. So I included this at the last minute because it's a favorite of mine. I'm always looking for some place to put it. This is a haiku by the famous Japanese haiku artist Basho. Too much mist, can't see Fuji. Makes it more interesting. Yes, often it does, because you can think about what it is. So, and I think so I'm just going to make two quick remarks about education here, because we're going to talk about this later. So I threw these in at the last minute. But I think one of the things we mistake then is we leave out that mist in our educational process. We develop these heroic narratives about science. My favorite is this sort of arc of discovery in physics, where you go from Copernicus to Kepler, Galileo, Newton, Herschel, blah, 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 all the way to Einstein, and kaboom, physics, there it is. A nice smooth arc, and that's all there was to it. But of course, this wasn't the way it happened. Actually, there was this rambling, confused, often failed, wrong, occasionally successful path of discovery that might have included these same people, but you know, it wasn't some nice straight arrow. They went off in cockeyed directions and things like this. There were long periods when kind of nobody could figure out what the next step was. There are a lot of forgotten names. I should say a lot of those forgotten names are the names of women. So Caroline Herschel, Marie Lavoisier, not just Marie Curie, but her daughter Irene, and Mileva Maric, Einstein's wife, and probably the better mathematician of the two. And so I think these are the kinds of stories that need to be told in our classroom settings and in general to the public. Oh, yeah, I know this is a little weird, but I thought I ought to give you at least something useful to take home with you today. So I'm going to include this here. How to hide a dead body. So here's what you do, just in case. You have a dead body, you go out to the local park. You go out to Cambridge Green here if you want, and you dig a nice hole about 8 feet deep, and you throw the body in the hole, of course. Then you fill the hole up, but you leave it just dirt and all the rest of that. Now the police come along, and they see this recently disturbed patch of ground that looks a bit like a grave. Oh, let's go get the cadaver dogs. So they get the cadaver dogs, and the cadaver dogs go wild over it. What they don't know is that you cleverly have, while filling this hole up, have buried a dead dog at 4 feet. So the police begin digging in expectation of finding a body, and indeed they do find the body of a dead dog at 4 feet, and off they go, right? So the question, though, is, how long will this body remain undiscovered? And how many of these bodies, how many of these cadavers are there in science? How many times do we in our laboratories do an experiment, get the expected result, say, oh, that's great, and tootle right along, not realizing there's yet an undiscovered result below that fabulous discovery we just made. So you could hide a dead body this way, but it's not a good idea to do this in science. What's the answer to any of this? I don't have an answer to any of it, but I would like to put in a pitch for what I call pluralism in science. So pluralism is an idea in political theory and in history and many other areas developed, I think, largely by Isaiah Berlin in the last century, a great philosopher at Oxford. But I'd like to see it applied to science, and I don't think we do a good job of that. I'll use a quote here from Niels Bohr. I know I have a lot of quotes in this talk, and I don't do this for the purpose of authority. I just think people who said something important shouldn't be left out of the conversation just because they're dead. And I also think it's important to recognize that the conversation has actually been going on for a long time, and it will continue to go on, and our job is to jump in, say something. So Bohr said the opposite of a falsehood, the opposite of a fact is a falsehood. But the opposite of a profound truth is often another profound truth. That's a hard one to wrap your head around as well. But it happens quite regularly, and we often don't let this happen in science. So Charles Peirce, a Cambridge-born philosopher, logician, mathematician, and scientist of the late 19th, early 20th century, considered one of America's finest in those areas, although a little bit of a strange character, compared science. He said, science is not like a chain, only as strong as the proverbial weakest link. That is, it's not a chain of facts where the weakest fact, the chain breaks. Rather, it's more like a cable made up of many delicate strands, each one quite fragile, but when bundled together of considerable strength. And that the loss of any one of these few strands here and there will not reduce appreciably the strength of the cable. And so the idea is to keep these strands going on and not worry about the few that, or even the many that don't work. So let me end this by telling you the story of my dog. This is my dog, in fact, but that's not what this story is about. This is an old Newfoundland named Orson out in his favorite environment, the snow of Riverside Park. But the story of my dog is about young Tom, a 7th grade student who's given an assignment to write an essay. Young Tom writes an essay called My Dog. He hands it in. 2 days later, the teacher comes back and says, but Tom, your essay on my dog is exactly the same as your brother's. Did you copy it? And Tom says, no, ma'am. It's the same dog. Yeah. So we all think that's ridiculous, right? But that's not what we do in science. We don't recognize that there are a large number, not an infinite number, but many, many diverse ways of describing the same dog. And every one of them has some value. Some have more value, some have less value, but every one has some value at least. So let me just end with these two last statements from Rita Dove, at one time our poet laureate. Failure is a favor to the future. And this from the poet E. E. Cummings, always the beautiful answer who asks a more beautiful question. And with that, let me ask you what your questions are. Thank you very much.
My job to tell you how to ask the question. Okay, stay. So that was wonderful, and I'm sure you have many questions. And so let me just tell you how we're going to do that. You see that there's a microphone here in the center aisle. So please just come to that microphone to ask your question. We'll be patient while people make their way there. And then just as you ask the question, people love to talk. So just try to be careful and ask a question pretty quickly. And we'll take as many as we can. So thank you.
Yeah, the worst thing is that I also love to talk, so try and make it a brief answer as well. Yes.
Could you comment on the fact that so many of your references were from the humanities, an area we tend to think is separate from science?
Well, I don't think it is, obviously, and I'm quite pleased to be able to put so many references to the humanities in there. I claim that this is a talk about science, and I think it is. And I talk about science because science is what I know, it's what I do. But I don't believe that it exists isolated from the rest of our culture in any way, shape, or form, and that almost everything I've said today could just as easily be applied to the arts, to the humanities, to any of them, and that many people in the humanities have thought about these questions very seriously. I have a number of friends, see, I'm going to go on too long, but real quickly, I have a number of friends who are philosophers of science, and one of the things they tend to worry about is, do we care? Do scientists care about what philosophers of science think? And I like to tell them, it doesn't matter. It just doesn't matter what we think about philosophy of science. I mean, it would be nice if more of my science colleagues thought philosophy of science was important, but I think science is one of the most important things we have in our culture. We are a scientific culture. If you think the Renaissance was important or the Reformation was important, the scientific revolution has had more effect on our lives than either of those things, really. And so why shouldn't there be a philosophy and a history of science? For the culture, not for scientists. Who cares about them, really, you know? So this is what I try and tell my philosopher and historian friends. Do it for the culture. Don't worry about us.
There's a paper out on the internet which might have been published in
sounds very dangerous.
reputable journal that had a title, I paraphrase, "The majority of scientific findings are false." And it was a paper about, I guess, statistics, and goes to the heart of, have we failed or succeeded, or how do we define that, particularly in fields where the evidence is in the form of numbers. And I'm just curious where this issue of maybe people agree that the supernova had this brightness, but not on whether the universe is accelerating. Maybe they agree on this pattern of epidemiological data, but not on the cure or approach to mitigating disease.
So this paper was about what's come to be called the replication crisis in science, the inability of a certain number of papers, and we can argue about whether it's a large number or a small number, but a certain number of papers that are published in scientific journals, legitimate, which can then not be replicated by another laboratory later on. And this is considered to be indicative of poor statistical power and a variety of other sorts of things. I gave a talk last weekend on this whole issue, so unless you want to reset the clock, I can't give you the whole answer to this. Except to say I don't believe it's a crisis. I believe that replication failure is a kind of scientific failure that's very valuable. I think I'm not talking about fraud now. Fraud is another story. Fraud in science is the only thing I believe the death penalty should be used for. So, because really it won't work if people lie. But I think many laboratories publish, there are all sorts of subtleties in here, but I think laboratories will publish a result that they generally believe in and they have gotten. If it can't be replicated by another laboratory, that often means that there was something they did they didn't even know they did. It was one of those, we didn't know what we didn't know. And now we know that we have to look a little deeper into this. The original data is probably reasonable evidence. It just needs more evidence. It needs a better look, a deeper look. Sometimes it'll turn out to be wrong. But I have a phrase from Charles Colson Gillespie, a great historian of science, who said, in science, revision is a victory. And I think that should hang on the wall of every laboratory. So that's how we get to these things.
You indicated that ignorance grows with knowledge. And is there any explanation as to why ignorance, regardless of knowledge, facts, consistently remains in the 38% and never changes?
In the 38%, I'm not sure what you mean by
In
that.
other words, ignorance does not, it seems that it doesn't change even when there is new facts, the new additions, etc. It still remains very within that range. It doesn't really.
Yes. So again, I think this is a different kind of ignorance than the one that I'm trying to talk about, which is more of a communal ignorance. It's not so much personal ignorance, people who prefer to disregard facts or see facts only in the particular way that makes sense to them. And I want to point out, I'm not making a political statement here. I know it sounds like one, but I'm not making a political statement, or at least I'm not making a political statement that says this is more true of those people on the right of center than those people on the left of center. Marin County is full of well-educated liberals who believe they should not vaccinate their children, and they're out of their minds. I mean, they're just as ignorant as all the rest of it. And so, you know, nobody has a hold on ignorance in that way. But that's a different kind of ignorance, I think, than the one I'm talking about. That's the low-quality ignorance. And that, I'm afraid, we may have to learn to live with. Yeah, I don't know.
So many of the quotations, the wonderful quotations you showed us today are historical, and you made already the point that you wanted to show that it's the great thinkers have been thinking about that for a while, right? So if that's the case, why, I mean, this is not a new realization, so why do you think it hasn't been taught, it hasn't changed the way to teach science, given that, again, we have been talking about that for a while, and I just was wondering, could it be that a more prescriptive way to teach it is actually more efficient, or that you would figure out that on your own at some point? Maybe it's a better way than telling you that you're going to fail many times.
Yes, so everybody has big questions, and there's this clock ticking away over here. Let me try and make a quick answer to that, and then I'd like to say that I will be around all day, so I'd be very happy to have discussions, especially at the poster session, which I intend to go to, because I think education is in many ways the key to this issue. Let me just say that I think the idea, educational reforms and ideas for educational reforms have been around for a long time. Most of what I said today, I think, is not new. As I said, John Dewey, in my opinion, kind of had this all figured out 100 years ago. To me, the question is, what's the obstacle to doing this? What's the obstacle to making these changes that we almost all see as obvious once you say them? And I think the main obstacles are evaluation and assessment. We need to evaluate, we need to assess students and how they do, ourselves and how we do, and the tools we use are old and decrepit and blunt and not very good. We need new tools for evaluating and assessing that include things like ignorance and failure and uncertainty and measurements of that and ways that students can develop in those areas, but we can still evaluate and measure. The only thing I will say positive about all that is that I think that's a scientific problem that's solvable. I think with computer science, with statistics, with probability, with game theory, and even including things like art auctions and economics and business valuation, we can learn to develop new methods of evaluation and assessment. So this is a problem that's solvable. We just have to get to it. Yes?
Hi there. So if my question as a lawyer is, when we're developing public policy, so what are the implications for both the development of policy, of uncertainty as to scientific facts, whether it's approving medicines or coming up with environmental policy, in terms of the substance of those policies, and also what should we be embedding in our policies to address, to account for the possibility that the initial facts on which the policy is based turn out to be wrong, and do you see something that we should be doing to address that?
Yeah, of course, if I had a prescription for that, I would have told you during the talk. And I don't have a prescription, and I think what we have to recognize is that it's hard work, that you do the best you can with what you have, that unsettled science, as I like to say, is not unsound science, it's simply unsettled. And as we improve it, we improve policy, but you do what you can with what you have, and that's been surprisingly successful, so why not continue doing that? There's a philosopher of science here at Harvard named Catherine Elgin who wrote a book called True Enough, in which she talks about felicitous falsehoods and that science is never completely true, is never always correct, it's just true enough is the important judgment to make. The longtime editor of Nature, a big science journal, John Maddox, the editor for some 20 years, was once asked by a reporter, so how many papers do you think Nature publishes that turn out to be wrong? And Maddox answered like that, he said, oh, that's easy, all of them. Because that's the case. They all should turn out to be wrong at some point. And so it's hard, I understand, to make policy on what you don't know is absolutely certain. But as I say, science has learned to work with uncertainty, and I think politics can learn to work with uncertainty as well.
I found your talk very interesting because you have a focus on ignorance and failure as fundamental to science. And it was very interesting to me because I disagree with that. And for me, the most important aspects of science are curiosity and discovery. And sometimes you don't discover what you thought you would, but that's still very exciting. And so I was wondering, why do you choose to focus, why did you focus on ignorance and failure as opposed to, say, curiosity?
I would say curiosity comes out of ignorance and leads to failure. So it's most typically. I don't want to leave you then with the idea that I don't think, for example, that knowledge is important. You need to know some things in order to get anywhere. As was pointed out, I think earlier, I think it was Alyssa who said, you know, lawyers, sorry for the lawyer, but lawyers don't make serendipitous scientific discoveries, scientists do. And biologists don't make serendipitous physics discoveries. You have to be working on something. You have to know something. So oddly enough, the higher the level of expertise, in my opinion, the higher the level of ignorance and failure, in fact. It's the experts who fail the most and who recognize how to fail the best. I don't want to dismiss curiosity. I'm really trying to kind of rebalance the thing because so much of what we think about science seems to be based on facts, big textbooks full of facts, potted histories of discoveries, and the idea that we don't fail, that we just go from great success to great success. And just to balance that, I'd like to simply suggest that if you want curiosity, curiosity does not, in my opinion, come out of textbooks and arcs of discovery, genius-made discoveries, as it were. But curiosity, imagination, intuition, inspiration, this comes out of, I think, a willingness to be ignorant, if you will, and a willingness to fail. I think we're talking about the same thing.
Stuart, that was fantastic. So as a scientist, I've had my many years of ignorance and failure. So I had a more general question. So for young researchers coming up in the field, they're not allowed to admit to ignorance and failure because of the pressures of universities and tenure and academic success is what is valued. So as a seasoned researcher as yourself, and I say that in the best way.
Thank you for making that clear.
How do we instill this idea that you can fail and be ignorant and still get tenure at Columbia?
Well, I did. Yes, it's an important question. I think this is, I really didn't have the time to develop it. I think it could be developed, and I think there are a lot of people working on this. I think this is where ideas of pluralism become so important, that there are so many ways to contribute, that, and again, it's a kind of an assessment and evaluation problem. So I don't think pluralism is actually a very useful thing at the bench, if you will. I mean, if I'm in the middle of an experiment, I don't want to be thinking of 20 other possible ways that this experiment could be done. I need to be dedicated and focused on that experiment. But in so much else that we do as scientists to support the scientific structure, such as promotion and hiring, curriculum, all reviewing papers, reviewing grants, all of these other things, I think a more a serious approach to pluralism in those areas would benefit the whole structure and all the people in it tremendously. Because they would allow of things like ignorance and failure. If you have really good ignorance, then if your questions are good, then I want you in my department. I don't care if you know the answers. I just want you in my department if your questions are good. And the better your questions, the more likely you are to fail. But you're likely to fail in creative ways. And some of those failures will be really useful to me as well. But I appreciate it. It's a very difficult problem because we have students who we want to promote along the way and all the rest of that. But somewhere along the line, they're going to have to learn that it's mostly failure and an awful lot of ignorance.
Stuart.
How good.
I think
Thank you very much. Thank you all very much. Yes.